Hello. In this talk, I'm going to present you Treaty. Treaty is a secure, distributed transactional key-value store that supports serializable distributed transactions with strong security properties. This is a joint work with Maurice Bailleu from the University of Edinburgh, Natacha Crooks from the University of California, Berkeley, and my advisor, Pramod Bhatotia from the UM. Let me now start with a brief introduction and the motivation for our project. So distributed systems are everywhere in the cloud, and distributed transactions provide us with a powerful programming abstraction. They allow users to execute operations in a serializable and atomic manner and process massive datasets that might be distributed in different machines. At the same time, they hide complexities such as data races and parallelism, and they offer fault tolerance. Distributed transactions come with very nice and strong ACID properties. The two-phase commit protocol is a standardized protocol for realizing distributed transactions. The client sends the transaction to a coordinator node, which is responsible for driving the protocol execution. The coordinator sends the respective requests to all involved nodes that are called participants. After the transaction execution, the coordinator executes the prepare phase to ensure the all or nothing property. For durability, both the coordinator and the participants log the transaction execution phases in the persistent storage. After the successful preparation of the transaction, the coordinator instructs all involved nodes to commit the transaction. Therefore, we see that distributed transactions require to heavily exchange messages over the network and log their state in the persistent storage. Unfortunately, offloading transaction processing in the cloud has increased the security violations. Malicious attackers that can compromise and gain control over the entire software system stack, but also any kind of software bugs and configuration errors, might compromise the security properties of the stored data and the executed operations. Therefore, under the presence of such a powerful attacker, we have identified two core threats in the context of distributed transactions: the secure execution and the secure persistency, which both refer to how can we materialize and guarantee durability and atomicity for the distributed transactions in the untrusted cloud infrastructure. Now, let's see these threats in more detail. Such a powerful adversary can tamper with the runtime data, the network messages, the operations, the protocol execution, and compromise the integrity and the confidentiality properties of the executed transactions. Therefore, our first question is how can we guarantee that distributed transactions will be executed in a secure manner? In addition, the adversary can also tamper with the recovery mechanism of the crushed nodes and compromise the consistency and the correctness properties. For example, tampering with the log files, they can perform rollback attacks and revert some nodes to a state, to an obsolete but valid state, deleting that way some parts of a distributed transaction. Now, since the transaction needs to be atomic and durable across reboots and restarts, we need to ensure both the crash consistency and the distributed rollback protection. In the rest of the talk, we refer to these properties with the term secure persistency. Therefore, our second question is how can we guarantee secure persistency for the committed transactions? To frame our problem clearly, we seek to design a distributed key-value store that supports distributed transactions with secure execution and secure persistency. And our proposal is Treaty. Treaty is a secure distributed transactional key-value store that supports distributed serializable transactions. In addition, we guarantee integrity, confidentiality, and secure persistency for the stored data and the executed operations. Lastly, we design Treaty with consideration to performance. So let me show you the overview of our Treaty system. Treaty data is divided and persisted across the system nodes in the untrusted storage. In Treaty, we leverage the advancements in trusted hardware, specifically the trusted execution environments, to guarantee all the aforementioned security properties, while we expose a conventional API for executing transactions to the clients. In treaty, we have implemented secure protocols for transactions to guarantee secure execution and secure persistency. Our protocols rely on trusted services that might run in the same nodes along with the treaty code or in any other node within the same cluster. We will discuss the use of the trusted services later in the talk. Now that I've motivated the need for treaty, I would like to discuss some background information on trusted execution environments and the system challenges. Trusted execution environments are hardware extensions that protect applications from untrusted entities, including a compromised software system stack, like an operating system. They provide us the abstraction of the enclave memory, which is a hardware-protected memory region that guarantees the integrity and the confidentiality of all residing code and data. In treaty, we build on trusted execution environments to guarantee security for distributed transactions. However, the problem with trusted execution environments is that they are not designed for distributed settings, for distributed systems like our treaty, because they do not extend their security properties beyond the trusted enclave. Therefore, as they cannot protect the network operations, the adversaries can compromise the integrity and the confidentiality properties of the transaction messages, but they can also violate consistency properties by double executing an already committed transactions through replay attacks on the network. Therefore, we see that trust execution environments cannot be applied out of the box to guarantee secure execution for distributed transactions. In addition, trust execution environments are not designed for stateful systems either, because similarly they cannot protect the persistent data and the logs. The adversaries can violate the security properties of the stored data, but they can also perform rollback attacks, and as we have already seen, they can compromise the consistency and the correctness properties of the system. Therefore, trust execution environments cannot guarantee secure persistency for the committed transactions. Now, let's see what treaty is doing. In treaty, we have implemented two protocols for transactions. A secure transaction protocol that guarantees secure execution for the transactions, where we guarantee the integrity and the confidentiality properties. In addition, we have implemented a stabilization protocol that guarantees secure persistency for the committed transactions, where we ensure that transactions remain crash-consistent and resilient to rollback attacks. Now, let's see what these protocols are doing. So, in treaty, we have implemented a secure two-phase commit protocol, leveraging the trust execution environments. We run the protocol within the trust execution environments to shield its execution and guarantee that the state transitions do not deviate from the protocol specifications. To extend the trust across the network and guarantee integrity and confidentiality for the transaction messages, we build on a secure message format. To sum up, treaty guarantees secure execution for distributed transactions by shielding the two-phase commit protocol and the network messages. In addition, we have implemented a stabilization protocol to guarantee that distributed transactions will remain crash-consistent across reboots and restarts. Our stabilization protocol is based on two trusted services, an attestation service and a trusted counter service, and we rely on three core principles. First, at initialization, treaty needs to establish trust among the system nodes. To achieve that, we leverage an attestation service that is also responsible for distributing secrets and any configuration data to the authenticated nodes. Secondly, after the transaction execution, treaty needs to ensure that distributed transactions will remain crash-consistent. To achieve that, we build on a secure log file format that allows both the coordinator and the participants to log their state and the transaction execution phases persistently in a secure manner. Now that the transaction is made crash-consistent, treaty needs to ensure that it is distributed rollback protected, namely that all parts of it are rollback protected in all involved nodes. To achieve that, we build on a trusted counter service. Our trusted counter service grants trusted and monotonically increased IDs to both coordinators and participants for their log entries. To sum up, our stabilization protocol guarantees secure persistency by relying on two trusted services and a secure log file format. So far, we've seen how the treaty overview and how the protocols are working, and now I would like to show you some of the implementation details of treaty. This is the system stack of a single node of our treaty system. In treaty, we have implemented a secure network layer with which we build the secure-to-face commit. In addition, we have implemented a secure storage layer for the persistent data, which is managed and accessed by a transactional key value engine. In treaty, we built a shielded network stack that offers low latency communication among the treaty nodes. Our network stack enables the direct I/O mechanism within the trust execution environments. Note that direct I/O is especially favorable in the context of trust execution environments because that way we avoid the system call execution, which is especially costly for TEs. Treaty buffers pass through an encryption-decryption layer, and our network library copies them to the transmission queues in the host memory, which are mapped to the network card's memory. In addition, we encapsulate some metadata to prevent replay attacks on the network. Our code base is implemented on top of RDMA and DBDK. To sum up, our network layer serves two goals. First, to optimize, and secondly, to seal the network operations. In addition, each node runs a transactional key value engine within the trust execution environment to manage and access the persistent data. We have an in-memory key value data store for the recent updates, and all other bulk data reside in the persistent storage in secure and authenticated files. To optimize for the enclave memory, our in-memory key value store divides the keys and the values in and outside the enclave respectively at the cost of encryption for the latter. In addition, we are compatible with both both optimistic and pessimistic single node transactions. Pessimistic transaction takes logs as they go along, where optimistic transaction rely on a validation phase that takes place at the commit time. Our code base is implemented on top of RocksDB. To sum up, our storage layer secures the persistent data and optimizes the enclave memory usage. Now, let me show you the evaluation of treaty. In our evaluation, we seek to answer two core questions. First, what are the overheads of the treaty-to-face commit protocol without any storage layer? This is to isolate the performance overhead for the secure execution of distributed transaction. Our second question is what are the performance overheads for treaty overall? We use Intel SGX as our trust execution environments, and we run treaty in a cluster of 3 SGX enable machines that are connected over a 40 gigabit interconnect. The plot shows the performance slowdown of the treaties-to-face commit protocol with reference to a native execution of the protocol. We ran a native execution of the two-phase commit with the encryption layer on, and to secure versions of the protocol that run within the trust execution environment with and without the encryption layer. Lower is better in terms of performance. In general, we see that the treaty-to-face commit protocol incurs about 2 times slowdown compared to its native non-secure execution. The overheads mainly derive from the trust execution environments rather than the encryption. The plot shows the performance slowdown of 3 versions of treaty systems compared to a native execution of a distributed version of RocksDB. All these 3 versions run within the trust execution environments. The blue bar refers to a secure treaty execution without the encryption layer and without the stabilization protocol. The red bar refers to a secure treaty execution with the encryption layer but without the stabilization protocol. And lastly, the yellow bar refers to an end-to-end treaty system that provides the full security properties. Generally, we see that for the read-heavy and the write-heavy workloads, the stabilization further increases the overheads. And that's reasonable because we have an extra communication phase with the trusted counter service. For the TPCC workload, we see generally less overheads. And that's because TPCC executes highly conflicting transactions that generally limit throughput. In addition, the yellow bar, where we have the treaty execution with the stabilization protocol, in TPCC incurs less overhead compared to a version without the stabilization protocol. That's because we were able to saturate that version with more clients. In generally, we see that treaty incurs 4 up to 15 times overhead, where the overheads mainly derive from the trust execution environments. We believe that future TEs will be able to further improve these overheads. To sum up, Treaty offers strong security properties with reasonable overheads compared to the state-of-the-art secure systems. To summarize, distributed transactions are an integral part of online services that are hosted in the third-party cloud infrastructure. Unfortunately, distributed transaction processing does not come without challenges. The state-of-the-art trusted hardware, trust execution environments are not designed to offer trust for distributed systems with transactions and untrusted storage. In this work, we presented Treaty, a secure distributed transactional key value store that offers serializable distributed transactions with integrity, confidentiality, and secure persistency. In Treaty, we extend the security properties of the TEs to the untrusted network and the untrusted storage, and specifically we build a secure-to-face commit protocol that guarantees that distributed transactions will be executed in a secure manner, and the stabilization protocol that guarantees secure persistency for the distributed transactions. Our code base is relied on trust execution environments and direct I/O mechanism for the networking. Lastly, our code is open sourced. Thank you.